Great, thank you all for being here. I'm James Ward. I'm a developer at Salesforce. So let me tell a little bit about how I got into machine learning. So I've been a developer for a long time, have some math in my background, but really am totally new to machine learning. So there's something called Salesforce Einstein, which is a suite of developer tools. And those tools include some things that I'm going to be using today to go through an intro to machine learning. So if you've never done any machine learning, I think this talk will hopefully help get you a little bit into it. So how do humans learn? I think before we talk about how machines learn, we have to talk about how humans learn. So what we do as humans is we observe the world. So we look around, we take in some data, we compare that data to our expectations. We make some assumptions. And then we analyze what are the differences between what we saw and what we expected. And then we refine our model. So I have a 1-year-old daughter, that's Josie, and it's really fun to watch her do this. It's kind of hard to see it once we get older for some reason. But my daughter, she does this all the time. So we put her in our high chair, and we give her some Cheerios. And so, of course, what she does is she grabs the Cheerios, and she drops them on the floor. And so then she waits to see what happens next. And so what happens next is we don't want the Cheerios on the floor, so we pick up the Cheerios off the floor and put them back on her high chair. And then she has just evaluated this model and said, okay, so when I drop Cheerios on the floor, the parents pick them up and put them back. So let me try that again. So she takes the Cheerios again, drops them on the floor, and we pick them up and put them back, and goes on and on and on. So it's a lot of fun to watch Josie and watch how she learns and how she's refining her model of the world. So with machine learning, it's really not that much different. What we do is we take some data and we create a model from that data. And then we look at that model and say, does it match our expectations? So we evaluate it. And then we take some feedback signals. So we take different parameters, we tweak some things, and we see, how does that change things? Did it get better or did it get worse? And then we can refine the model and make it better. So that's really what we're trying to do with machine learning, is to do what humans are doing all day long, every day, what Josie is doing with the Cheerios. We're trying to get computers to do that. So ultimately, this is kind of like doing pattern recognition with ones and zeros. It's all ones and zeros, right? So what we're doing is we're taking some data, and in the old way that we would do this, we would maybe build up a logic structure with a bunch of if statements, and then we would be able to make a decision. But that's not a very good way to learn, because that model is hard to evaluate. It's not very flexible and hard to reuse, those sorts of things. So what we do now with machine learning is we take data, we apply an algorithm to that data, and that creates a model. So then we get out of that a model. And the model is what then we can ask questions to. So we can then ask that model and say, give me a prediction or give me a categorization. So that's the way that we do machine learning now. And machine learning is a giant space now with lots of different fields and subfields within it. So there's unsupervised learning, supervised learning, reinforcement learning, are kind of the broad areas for machine learning. So it's a very wide field, and I don't think anyone really knows all of it. So as developers, what we need to do is figure out, okay, how do we use the pieces of this that are going to help us accomplish what we need? So that's where we start, is what are we trying to accomplish? What is the pattern that we're trying to learn from? What is the decision that we're trying to get out, or the prediction? So there's use cases like search relevance or collaborative filtering, decision support, time series forecasting. So those are the things that we're trying to use machine learning to do. Then we have some core methods that we use to do that. So the core methods are compression, classification, regression, and reinforcement. And we'll talk more about those in a second. And then there's some frameworks that allow us to do those methods. And so the frameworks are usually pretty serious math, I'm not ready for that side of machine learning yet. Maybe never will be. That's for the mathematicians and the statisticians to figure out how to do those sorts of things. But what I can do as a developer is I can figure out what are the methods that are going to work to allow me to solve the problem that I'm trying to solve. So what are some use cases that I would want to solve? So I want to rate my sales leads with how likely they are to close. So I can do that by taking in some information about that lead, looking at past leads, and seeing, based on what happened in the past, can I make a prediction about how likely these leads are going to be to close in the future? I can do categorization of text. So I can categorize text as offensive or not. I can recommend products based on what I've liked. I can detect anomalies in credit card purchase behavior. So those are just some of the many use cases that I've started working through on various projects to see how can machine learning help me with these tasks. Now there's the methods. I just want to go through these quickly. I won't spend a lot of time on them, but compression. So what we're trying to do with compression is determine the pattern. We're looking for the pattern in the data. Then classification, determine if this thing is an X or a Y. So that could be, in our Salesforce Einstein product, we have something that was called MetaMind, now called Predictive Vision Services. And what you can do is you can give it an image and ask it, is it a cat or a dog? And it uses a bunch of images that you've fed into it and classified already, and then it'll tell you it's a cat or a dog, right? Regression, determine the correct output for an input. Reinforcement, determine what action yields a reward. And so those are the main methods that we have available to us to build our machine learning on top of. So if what sometimes people look at machine learning and they kind of think it's this magical thing and it can do anything for us. There's a lot of hype around machine learning, and so I work with salespeople, and the salespeople are always like, "Oh, I've got this customer, and they want to use machine learning to tell them how to pull more money out of the system or whatever, right?" And it's machine learning is not magic. It's not going to be able to come up with stuff out of thin air for you. So if you're machine learning, what you're trying to solve doesn't fit into one of these models, then it's probably going to be pretty hard to solve. So definitely use these models as a way to gauge, is it possible? So one of the very typical use cases for machine learning, it's the one that I'll focus on today, is product recommendation. This is also called collaborative filtering. This is one of the things that I've realized about machine learning is that there's the mathematician names for all the different parts of machine learning. And these names haven't really been developerified yet or made more accessible to people like me. And so if you hear the term collaborative filtering, just think product recommendation. And you'll come across this in all sorts of places in machine learning where there's these fancy words for things, and it makes it kind of hard to understand. So collaborative filtering is product recommendation. So what we're going to do with product recommendation is we're going to take a bunch of user likes. So users have liked something. They've liked a movie. They've liked a house. They've liked something. We're going to use that data to make a prediction about what else the user might like. So that's where we're going today. So with that, let me show you a demo. So this is a little demo app that we built. It looks a little funky on this screen because it was made for a mobile device, but we can use it anyways here. So in this little demo app, what I have, let's reload it, make sure we're all up and running. And what I can do is I can browse through some properties. So we can see, here's some properties that are for sale in Boston, and I can see some information about them, the bedrooms and bathrooms and asking price. And then I can favorite this property, right? So I can add it to my list of favorites. We can go and see our whole list of favorites. So these are all the properties that I've favorited. And then if I go down to this tab, recommendations, that's actually now going to a machine learning system and asking the machine learning system, give me the other properties that I would be interested in. So I gave it some favorites, some other users gave it some favorites, and so now what we want to do is take all that favorite data and produce some useful recommendations for the user. So pretty simple example here, but it gives us a nice tidy way to dive deeper into how we would actually build this type of system with machine learning. So we could certainly do a lot of hard coding around this, and that's what I think we were trying to do as developers for a while, is use logic trees to give us this type of recommendation system. But what we want to get to is to a model that we can ask questions to that model and get answers back out. And so that's what we're going to go through today. So how do we get to that actual model? So for that demo that I just showed you, let me just talk about a couple of the pieces of the puzzle real quick for what was going on there. So to get the recommendations, I'm using Prediction.io. It's an open source machine learning server. I'll talk more about that in a little bit. I'm running it on Heroku. I use Heroku Postgres. That's a relational database managed in the cloud. And then Heroku Connect. So one of the cool things in this particular demo, which I won't go into the kind of back office process part of it, but I want the favorites data to also be in Salesforce, so then my salespeople can do campaigns around what users have favorited and do some analytics and reports and those sorts of things. So that was, we use Salesforce and Heroku Connect for that piece. I'm using Apache Spark, which is a big data framework I'm sure many of you are familiar with. And then I'm using Spark ML, so that's my machine learning libraries that are built on top of Apache Spark. So that's what that particular demo is built with. And all the code's up on GitHub. I'll give you the link to that in a little bit. Okay, so we're going to talk about product recommendations. How do we get to product recommendations? So I think a lot of times when we break down machine learning, we need to start with, how would we do it as humans? How would we recognize the pattern as humans? And so let's take an example. So I've got a grid of users, and I've got properties. And these users have favorited these properties. So user 1 has favorited property 1 and 2. User 2 has favorited property 2 and 3, etc. So just by looking at this, we can probably guess that it's probably likely that user 1 should be interested in property 3 because both user 1 and user 2 like property 2. So they have something in common about what they like. And user 2 also likes property 3. So now we should be able to infer that it's likely that user 1 will also like property 3. Okay? So we've recognized a pattern that usually when users like something that someone else likes, then they're going to like other things that person likes as well. So likewise, user 2 probably will like property 1. User 2 will also probably like property 4 because they have something in common with user 3. And then users 3 and 4 will probably like properties 2 and 3. So that's just, first tier of what we would expect for what these users would like. So there's another one here. Second tier is user 1 has something in common with user 2 who has something in common with user 3. And so user 1 will probably, or not, maybe not probably, will kind of possibly like property 4 because user 3 likes property 4. Right, so we can make some other kind of second tier assumptions. So we're just doing learning in our head. We're looking at the data. We're creating a model, and then of course we could test this model and see. We could ask user 1, hey, do you actually like property 3? Is that accurate? Right, so we could put feedback into that system. Okay, so pulling back this a layer. To do product recommendations, really what we're doing is we're probably saying that, okay, there's some traits to properties, and there's some traits to what users like. So for properties, there's, does it have 4 bedrooms? Is it near a park? Does it have a good school? Does it have good views? New build, right? And then users will like or rate those different factors, right? And so usually when I like something and you like something, then it's because there's some factors there that create that commonality. So it could be that, I really like to be near a park, and another user really likes to be near a park, and that's why we have something in common. That's why we like the same properties. So it turns out if you have this data, so if users have actually told you all the things that they want, and you know the traits on the properties, then you don't actually need machine learning, because you can figure it's just really simple math at that point, right? It's essentially doing a search. So the reason why we want to do machine learning is when we don't know these things. So the way that we do that with product recommendations is we take the user's favorites. That's the only piece of data that we have. And we're going to think through this first just as humans without applying the machine learning to it. So we know users' favorites. If we know users' favorites and we know the property features, so we maybe only know one of those, or we know the features, we know the property features and the favorites. Then we can use both of those things to determine the third thing, which is the user features and how each user would value certain things. So the way that works is we're going to look and see, okay, does user 2 likes property 2 and 3? So what features are there in common between properties 2 and 3? And if there is features in common, then we're going to say, okay, the user probably likes that feature because they liked that property that had those features, right? So that's how we can use the features and the property, the favorites and the property features to basically guess what the user features are. Likewise, we can take the favorites and the user features and guess what the property features would be. So what we're saying is that there's a correlation, and there's essentially an equation that we can apply, that we would apply in our heads to do this, and we can apply that equation with computers. So then there's another step to this, that is, if we have the property features and we have the user features, then we can do some math to determine what recommendations to make. So we're essentially saying that this property has these features, so it is by a park and has nice views, and the user wants to be a house that's near a park and has nice views, so now we can make them a recommendation based on that data. So if we can get to property features and user features, if we can have both of those, then we can get to recommendations. And that's why if you already have these ratings, so if your users have told you what they want, the features that they want, and you know the features of the house, then you don't need machine learning, right? That's just a very simple mathematic equation that I don't understand, but somebody understands and built for me, that we can use to determine our recommendations. Okay, so we don't have in a recommendation system, we don't have the property features and the user features. So what we're going to do is take that favorites data, and somehow we want to get from the favorites data that we've been given and create the property features and the user features. So that's what we're aiming for with machine learning, is to be able to go from just what I've favorited to both of those sets of features. So it turns out it's possible to do, and some smart mathematicians came up with a way to do it and do it efficiently. That's usually a big challenge with a lot of machine learning problems, is that you can think of ways to solve the problem, but it may not be possible to solve it at the scale that your data is at, because it can be a lot of math. Okay, so here's what we do. We use an algorithm called alternating least squares. So alternating least squares is a mathematical algorithm that fits this problem very nicely. So what we're going to do is we're going to generate some random data for our user features. So we're going to just randomly say, user 2 likes the houses with the nice views, right? And we're going to go through the whole matrix and we're going to fill it with random data. Then we have our favorites, so that's the data we do have. So we're going to use the favorites, and remember there was a correlation. We could know what the property features were if we had the favorites and the user features. So we can do that calculation. So we're doing it on random data. So we're taking the random data for the user features, and we're applying that to what the users actually favorited, and out of that we get the property features. So it's kind of random still. So what we do, and when we do that, the reason why it's called least squares, why least squares is in the name, is because there's a mathematical way to say, to optimally generate that property features matrix. So the matrix is just the table of data. So there's an optimal way to do it that essentially reduces the error between what we've generated or what we've calculated and what it would really be, okay? So that's the least squares part of this. Now the alternating part of this is that then we take what was created, so that optimal, where we are in the process, we take the optimal property features, and we feed that back into the system. So what we do is we take that one, and remember there's a correlation between the property features and the favorites, allowing us to calculate back to the user features. So now we have this circle, so we can take what was optimally generated and feed it back through, and then do the same thing again. So we keep iterating through this loop to generate the features for both the users and for the products, so that then we get our model. And that's ultimately what we're trying to do. So we repeat. And even though we started with random data and filled that first matrix with random data, because we were essentially converging the model to something that fit the favorite data that we have. So that's part of the cycle, is to always look and see how close does taking the user features and the product features and determining recommendations, how much does that fit to what the users told us they actually liked, right? So we're constantly testing the model, and because of that, what we're doing is we're converging the user features and the property features to a model that fits the favorites data that we have. And that's called training data in machine learning. So that's alternating least squares, and there is a bunch of math underneath that makes that all work. So luckily for developers, a lot of this stuff has actually been abstracted into libraries. So by using the libraries, I don't have to know all that math underneath the covers. And because this is built on Spark ML, it can now go out across a network of Spark computers, Spark nodes, and be able to process this stuff in parallel. So smart people have put together that piece of it. And but I think it is important to understand some of the basics of the algorithm, because there's an important part of this, which is pretty cool. So it turns out that it doesn't even really matter what the features are. We don't need to know that there is a house has a trait that is by a park, or that the user likes the houses with the views. We don't even care anymore what those features are. So what we're doing is we're just going to say there are features, and we don't know what they are. We don't need to know what they are. But we're going to put in these, start with random values. We're going to say that user one likes houses with views, and then we're going to iterate and improve the model until we get something that fits with what they've actually told us they like. So it doesn't even matter what the features are, and we can have as many features as we want. So that's the alternating least squares algorithm and how that works. So how does this actually get us to a recommendation? So this is just a little bit of math here, but once we have our user features and our property features, so that's just the correlation between property and features, right, and user and features, then we can do a little bit of math to figure out how to make an actual recommendation or a likelihood that this user would like a particular property. So the way that we do that is through using dot product, which is a matrix math thing, and we take each column, so each feature, and we multiply together the values. In this case, with liking something or favoriting something, it's binary, just on or off, but this could also be numerical digits, so it could be that they gave it a score of 5 or whatever that may be. So in this case, I'm multiplying together the columns, and so in this case, the correlation between user 1 and property 1 would be a 1, because I'm going to add up all those values, and I'm going to get a 1, right? And so you can see that the more places where there's overlap between the user features and the product features is going to be a higher recommendation or more likely recommendation. So that's the dot product math to be able to do that. So ultimately what we can get to is what's called a matrix factorization model. And all that that's saying is that we've gone through for every user property pair in our data set, and we've calculated that dot product on each of those. So, and then we can fill a whole matrix with the recommendations. So we can say, hey, user 1, now you have, let's say, 90% likelihood of liking property 1. And remember, that all came from having the user features and the product features as the way that we were able to get to this recommendation. And remember, the user features and product features were randomly generated and then converged to what the users had told us they actually liked. So that's how we do machine learning on this type of data set for doing product recommendation. Okay, so enough mathematical stuff. Let's talk about code. So the nice thing about this is that it's been made pretty darn easy by SparkML. So in this case, I'm going to start with a list of favorites. That's my favorites data. SparkML wants that data to be in the form of a rating. And so I do need to do some transformation on my favorites to get it into a rating. You'll see that I'm putting a 1 inside of there. And if this was like a rating like on a scale of 0 to 5 or whatever, then I'd put that value in there, right? So I get my ratings, and then in the case of SparkML, I do need to actually wrap that up into an RDD for Spark. But then all I have to do is run als.train, and I give it my ratings, and I give it my rank. My rank is how many feature columns am I going to use? So you could probably guess that if I use less feature columns, then I'm going to get less accurate predictions. If I use more feature columns, then I'm going to get more accurate predictions. The downside to using more columns is that then it takes a lot longer to calculate and uses more disk space and those sorts of things. So in this case, let's just say that I'm going to do 5 feature columns, right? So again, SparkML doesn't care what the features are. And this is kind of something that stumped me. It's like, really, I don't have to give it like how many bedrooms these things have. And it's like, no, because it's going to essentially model the data without knowing what those features are. And that's the whole point of the machine learning in this case. Okay, so we run the training. What we get out of that is our user features and our product features. And then remember, once we have the user features and the product features, then we can make a recommendation. The way that we do that is that dot product math. And so we can do dot product math on every user property combination, or we could do it on demand when somebody asks for it, up to our use case. So if we did want to get a recommendation out for a specific user, then I would maybe create my matrix that has all those ratings in it, and then I could filter out that matrix based on a user ID, and that would tell me what properties I'm most likely interested in. I could also filter it out based on what properties, and that would tell me what users would be most interested in a specific property, so I can go either direction. Okay, so that's a quick overview of the code, but let's go and actually look through the real code so we can actually see this thing in real life. Okay, so here's my dream house recommendations app. It's written in Scala, and I have a train method. My train method takes my favorites. Those come, in this case, from a web service, but obviously you could get those from wherever. I have this reg param, and this one is something that's part of the algorithm. It's a tunable part of the algorithm that's basically how much you want to weigh the extreme values. In my case, I don't really have extreme values because I'm using just on-off, right? And so, so this one I turned way down. Basically, don't weigh it, okay? And then I have a rank, which is my number of latent features. So that's the number of columns, essentially, that I'm going to have for features. So in this case, the default will be 5. And then how many iterations do I want to do through alternating least squares? So remember, alternating least squares is starting with a random user features, then calculating the product features, then using the calculated product features to then recalculate the user features, and doing that over and over and over again until we converge to a model that fits our training data. Okay, so in this case, 10 iterations through that. And again, there's going to be lots of trade-offs with this. I could increase the iterations and get more accurate results, but it will have a trade-off of costing me more CPU time. Okay, so we're going to get our ratings. We're going to get those into an RDD. Then I'm going to run my ALS train. I'm going to give it my ratings. I'm going to give it those parameters to the algorithm. And then what I get out of that is going to be my user factors, and I called it item factors, but that's the property factors. Factors, features, similar. I think that's the same thing there, so you can name them whichever you want. And then, in this case, what I wanted to do was I wanted to not just stay with those user and product features, I wanted to get to that matrix. So it'd be really easy to ask that matrix for a prediction for a specific user or a specific property. So to do that, now I had to write a little bit of math. So I essentially had to go through every cell in the matrix and calculate using dot product math what is going to be the value of that prediction. So remember, we talked about how we would actually do that with going through each row for the product and each row for the user and doing that math to multiply and then add up those different things. So that's all part of a library here called BLAS, and that S dot is that dot product on a matrix. Okay, but then what I get out is my prediction value. And so then I say, okay, I have now a pair, which is my property and my user, and I get a prediction for that. And so that becomes a map that goes into my model. So in my model, I store the user factors, the item factors, and my prediction map. Okay, so that's my training. So training and prediction are totally separate things, and you really want to keep them separate in this type of system so that I can train my model, let's say, once a night, or I can have my data scientist training models and tuning models and figuring out the best way to make those work. But then I want to be able to, at any point, and with a lot higher volume and a lot lower latency, ask the model questions. And so this is where I'm going to ask, I have a predict function where I'm going to give it the model. I'm going to give it the user ID and the number of results. And I'm going to go to my matrix factorization model, and I'm going to look up that user ID. So I'm going to basically say, all right, if the user, if I'm at the record that is for this user ID, then get me the property and the rating, okay? And then I do some transformation so that I get a nice little map that is a map of, in this case, the if I could understand my own Scala code, that would be wonderful. In this case, I think it's still a tuple of property and user ID. Or no, actually, just going to be, we can look at the type system for that. Come on, Scala is better than that. Okay, map from string to float. So that's going to be my property ID, and then the rating for that property ID is what I'm getting out of that. Okay, so that's my predict, and then I've got some other stuff in there to expose that as a web service so that I could use that however I want. Okay, so that's all the code I had to write to be able to create my model and then make predictions based on my model. So let's take a look at my tests. So a big part of machine learning is being able to evaluate, did this model do what I expected it to? And there's some different ways to evaluate the model and tune the model. I can tune parameters and those sorts of things. So in this case, what I've done, the way that I'm testing the model is I just wrote some unit tests because I thought that was an easy way to see what was going on. So I had to draw this out in ASCII because that helped me understand what I was trying to do. So these are my favorites in my system or in my unit tests. And so user 1 has favorited property 1. User 2 has favorited property 2, very similar to what you saw earlier. And then these are kind of like what I'm going to expect out of the system, like the predictions that it's going to make. And remember, we talked about those earlier. So then I have to model this into some code. So I create my favorites that create this model, right? So I create those favorites, and then I'm going to run some tests. So I'm going to run that train method on my favorites, and I'm just using the defaults, which was like 0.01 reg param and 5 features and 10 iterations, right? So that was just the defaults on there. So then I'm going to look at my user factors, and I'm going to see that my user factors should have 10 rows, one for each user, or sorry, 5 rows, 5 rows, one for each user. Because if we look at my data set, I have 5 users, right? And my item factors, those should also have 5 because I have 5 products. And then my matrix factorization model, where I have a map that's going to contain every tuple, every pairing between a property and a user, and have the rating for that. So that should be 5 times 5. So that I'm testing that, and then there's a few other things I'm testing right here. So if I look back at what I'm expecting, let's see, we're looking at property 1. So for property 1, I'm expecting that user 1 has favorited that, so that should have like the highest rating. User 2, we're going to infer, should be interested in that, so that should have a rating that's pretty high, but not as high as for user 1. And then if we look at user 3, not a very high likelihood that they're going to like that one. A little bit, because there is a commonality path there, but so we are going to pull those values out of our matrix, and then we're going to run our test and see, okay, P1 U1 should be greater than P1 U2, P1 U2 should be greater than U3. Okay, so let's just run this thing so we can make sure that this all works. So I'm going to run the test. So now it's going to go off, and it's going to start up Spark, and it's going to do the training of the model. So it's going to load that tiny little data set and then do all that math on that data set using the alternating least squares for 10 iterations, and then it's going to go through my test. And you see I have some other tests there as well. So good. So that all worked. So that's good. Things were as we expected. But let me uncomment this, and so we can actually see what some of the models actually look like underneath the covers. So we're going to look at, rerun this. We're going to look at what does the item factors actually look like? What does the user factors actually look like? And then what does our matrix actually look like? So we'll be able to actually see those visually, and I think that helps show like how the math is actually there underneath the covers. So here we go. So here is my user factors. So you'll see that each user has a row. So this is essentially just a matrix. And then we've got our user factors. So these are what the model has determined, what factors the model, how the user would rate the factors that the model has created, right? So again, remember that started with random data and then converged to a model that fit the favorite data that we'd supplied. So this doesn't in any way, you can't like visually look at it and be like, oh, now I can see like how that works. It doesn't, it doesn't really make any sense to us because the columns were just a way to do this calculation. And then we do the same thing for properties, so we get our matrix, right, of numbers. And then here we can see what does make a lot more sense is the pairing between users and properties, and then the actual prediction. So we can see that for property 4, user 4, the user supplied a rating of 1, and the prediction was almost 1. So that's good, right? That's what we would expect. And we can look through this and see. We can look and see, okay, property 4, user 2, got about 50%. So if we go back and look at, which one was that? Property 4, user 2. So property 4, user 2, you'll see that was one that we kind of inferred should have some relevance to the user because there was some commonality between user 2 and user 3. So sure enough, the model does show that, yep, it's not 100%, but there is some commonality there, and so the user should be interested in that particular property. Okay, so that's all cool and good. You can see what that matrix actually looks like. There's a couple other tests in here. Just point out a couple of these. So one of the things that I want to do is start tweaking those parameters, like the reg param, and seeing, does it fit my expectation? So if the train should be more accurate for higher ranks. So rank is the number of factors that we're going to use to calculate that model. And so if I go from 1 to 10, then I'm going to do a mathematical operation on that, and I will expect that the 10 one is going to be less error prone than the 1 one. And the test validates that that is in fact true, that there's less error in the one that got 10 iterations versus the one that got 1 iteration. So, and then it should also be more accurate with more iterations, factors, and then this one is iterations. So that's what we have the model, we're testing it, and it's fitting what we expect. So that's all good. Okay, so that code is all up on my GitHub, github.com/JamesWard, and then Dreamhouse Spark ML. So let's talk a little bit about deployment, because that's one of the challenges that we have as developers, is figuring out, that's great that I can run this all on my laptop, but how do I actually get it into a place where I can, like that Dreamhouse app, actually pull up the recommendations and get those? So in this case, I've deployed it on Heroku, and you can do that. You can also run Spark ML on your own Spark cluster. So up to you how you want to do that. And then there's some questions, like when do I actually run the training? Right? Do I do that nightly? Do I do that weekly? Do I do it hourly? But you do need to have some process that's going to periodically refresh the model, because the data, your training data, is going to be changing, and so you do want to be refreshing the model. And then oftentimes, when you get really serious about this, about doing product recommendations, you'll probably end up writing a whole nother algorithm, using a different algorithm to do recommendations, and then you'll start doing some comparison across the different models, or maybe tweaking parameters on your algorithm and seeing, is this providing better results than the previous one? So then a question is, where do you put the model? So when I create this model, I now have a bunch of data that I need around so that any of the web nodes that I have that want to be able to provide a prediction, I need to be able to use that model, right? And so that can be a challenge. Like, where do I put that? Do I put that onto disk somewhere and then share it across nodes? That requires serializing it to disk. Do I put it into Hadoop or a database? So this is what Prediction.io, the open source machine learning server, is doing for us, is it's giving us the way to train the data, persist the models. It actually puts those into Hadoop or a database, and then we can select between different models. We can tune the parameters of the model. So, and then it has some cool features like an event server. So a lot of times we need to feed some data into our system so that then we can pull it out to do our ML on. And so Prediction.io provides an event server built on Akka HTTP for doing that. And then you can build it on top of Postgres, Hadoop, or MySQL as the data stores they support right now. So the way that I got into machine learning was I was thinking about what problem do I want to solve, and it turned out the problem I initially wanted to solve was product recommendation for Dreamhouse. And so what I did is I went to the Prediction.io template gallery, where they've put together, I think there's like 50 or so different templates, machine learning template applications. They've put together a whole gallery of these. And so I went and looked for what's the template that best fits with what I'm trying to do. And there's Java ones, and there's Scala ones, and there's Python ones. So you can also pick the language that you want to do it with. So great place to figure out if you want to go from, all right, I have a use case, and I'm not sure how ML is going to help me solve it. The template gallery on Prediction.io is a great way to answer that question. Okay, the event server, model persistence, engine tuning, and versioning. The versioning is interesting because when you create these models, you may want to keep them around so that you can always then go back to the model, and maybe you've been comparing the different models and you realize this previous one was actually better than the new one. So Prediction.io provides a way to just switch back to the old version of your model, that sort of thing. And then Prediction.io has the REST endpoints for giving you those predictions. So. Okay, so that's Prediction.io. Check it out. It's open source. It's incubating Apache project. So cool stuff. Okay, I think I have a couple minutes left for questions. So I think there's a microphone that'll go around. If anyone has any questions at all, it may be really hard to see you, so wave your hand, stand up. Kirk has a question. Trolling me?
Yes, so let's start trolling. So let's not. What are your experiences about processing like time series data with these types
on
of
time
models?
series data? I haven't done ML on any time series data, so I am totally new to this world, and prediction was the first one that I tackled. But the Prediction.io template gallery does have some specifically for processing time series, and probably what you're trying to do in that is find some commonality or find outliers, those sorts of things. So that would be a great use case for machine learning. But yeah, I'd go look in that Prediction.io template gallery as a way to find an app that does something similar to that. Yeah. Happy to work with you on that. Other questions? Okay. All right. Well, I'll be around if anybody has any questions, but I hope that was useful, and thank you so much for coming. Thanks.